Okay. So this is work done with Rohan and based on this paper, which is going to come soon. So I'll be talking about particles which aggregate and this input of particles from outside. And I give a few examples to motivate the model. So first example is river networks. So this is like the mountain and this is like the sea. And rivers move around, and when they meet, tributaries meet, they become bigger rivers. So if I think about the direction of the river as time axis and the orthogonal direction as x, then this is like diffusing particles aggregating, and rain and other input is like input of small particles, small amount of water from outside. Similarly, if you look at rain formation in clouds, you have droplets of water inside the clouds and they coalesce, become bigger till they reach some critical size when they fall down as rain. Another example which is common is soot formation. Dust particles aggregate over time till they form soot in the corners of houses and so on. And this is an example from ductile fracture where voids are nucleated and they grow by coalescence. So a different spectrum, different kinds of physical phenomena have both aggregation and input. And these days there are a lot of examples from experiments in biological systems. So this is one example of cells being input and they coalesce, and you can track them using dyes and so on. So what is one quantity, experimentally, what are some of the things people measure? So one thing you can measure, like in this experiment, is how many particles are there of mass of size m in the steady state or at certain time. And typically when you look at the log-log plot like this, it's a straight line saying it's a power law. And in this experiment, the power is roughly 1.4. So now I'd like to, I will look at a well-studied model, which has been a very simple, well-studied model. It's sometimes called Takayasu model, sometimes Scheidegger river network model, and so on. So consider a lattice in which you have a certain mass at each site. So if I want to specify a configuration, I'll tell how much is the mass at each site. In this example, it is 3, 1, 0, 2, 0, 5, 3. Then I have to give the rules of evolution. So the dynamical rules are diffusion. So with some rate d, a mass hops to the neighbor, like if this 3 went to the right. And input is with rate j, a unit mass is added at the site, like this one. So now the system evolves in time. So one of the key features of this model is that aggregation creates larger masses, input replenishes the smaller masses, and the net result is a power law. Like in a simulation, if I measure the number of particles against m on a power law, and it happens to be 4/3 in one dimension. Since the power law comes automatically, this model has been studied as a model of self-organized criticality and so on. But there's another feature that is quite also of importance, is the analogy to turbulence. So in this power law, you have forcing at small masses, that's the input of particles, and then the particles move down the mass scale by collision. And like the example, like the talk Ritvik gave in the morning, you have turbulence in which energy is input at the largest length scale, smallest k, and there is some nonlinear interaction driving the energy down the k scale. So the analogy is quite perfect. It is there's a conserved quantity which is driven down the mass scale here and the k scale here. And if I make this analogy, then it becomes, some other quantities also become interesting, not just a single point mass distribution, but joint distributions also become important. Now, what is the question I'm looking at in this talk? So most studies are focused on the infinite system. So what they do is they take L going to infinity first, and then large time. So what is the phenomenology for finite system, which is the opposite limit? I take a finite lattice and then take the limit t going to infinity. So why is this question interesting? One is, most systems are confined. And second, in the turbulence analogy, you can ask what happens to scaling exponents when there is a competing spatial mass current as in this finite systems as opposed to a current in the mass space. So finite systems are two kinds: periodic boundary conditions where the mass is conserved and keeps increasing with time, and open boundary conditions when mass comes to the edges and they hop out both ways. So what is known? So there was a paper by Negi, Pereira, and Burma who talked about who worked on this problem a couple of years ago. So suppose you measure numerically the total mass in the system. That will increase linearly because you keep inputting mass at a constant rate. But then you subtract out the largest mass, and now you measure total mass when it's largest mass as a function of time. And you see it increases linearly and then saturates, okay, and reaches some sort of steady state. So that gives a picture like this. So on a periodic boundary condition, after a long time, all the extra mass goes and sits on one big condensate, which keeps growing with time. So that's the first statement, that in a periodic boundary condition, there's a condensate that breaks translation invariance. Secondly, they argued that far away from the condensate, there's a power law of 4 by, this is all in one dimension, n to the 4 by 3. And near the condensate, there's a power law which is different from this and roughly equal to 5 by 3. So there is a depletion near the condensate. So what did we do? We could do an exact calculation for this model and show explicitly that for a periodic boundary condition, it is actually 5 by 3 here and 4 by 3 in the bulk, 5 by 3 in the depletion zone. In the periodic boundary condition, in the open boundary condition, it is 5 by 3 near the edge, 4 by 3 in the bulk. Okay, these exponents are the same. And it's not surprising because, you can take a problem with a condensate, cut that site, and say that all the particles that come here get absorbed here, which makes it exactly equivalent to this problem, except for the fact that the condensate sometimes hops to the left and right, but that does not seem to matter. Okay, so we also did found exactly the joint distributions. So for the problem on the periodic boundary condition, we showed that probability of finding particles of mass m on the first site and the second site goes as m to the power 11 by 3, but here it goes as m to the power minus 4. I'm almost done. Minus 4. In the bulk, it goes as minus 1 by m cube and 1 by m cube. So even though the equivalent, there wasn't seem to be an equivalence, but if I look at joint distributions, the exponents are different. And so the equivalence between boundary conditions break down. And we can determine exponents also for the endpoint distributions, not by guessing and through numerics. So, so for this aggregation problem with input, we calculated the edge and bulk exponents. This part I'll leave. These are generalizable to mass-dependent diffusion. So the particles, all particles don't hop with the same rate. If the rate increases with, if the rate is smaller for large masses, then the condensate is fixed and the boundary conditions become equivalent. Based on our understanding, we can conjecture for 2 dimension. It says that in the bulk, you get 1 by n to the power 3 by 2 with a log correction. In this edge, you should do 7 by 4, and here it is 2. And one could also look at other models with condensates and look at the depletion zone and figure out what is the exponent that is are the exponents same, or do the condensates change its environment in a noticeable fashion?
Questions?
Yes.
In terrorist attacks, it is known that there is a power law in number of deaths. So new terrorists keep coming in, and then terrorist groups split, and then they coalesce. All that happens. So can terrorist attacks be modeled by this Takayasu model, that new terrorists keep coming in and terrorist groups have this both splitting as well as coming together?
Yeah. So I would say this particular model is there. Whether one can model that by that depends on, whether I can model, I cannot answer, but depends on the phenomenology there.
Can you also predict the fraction of particles in the largest cluster, or is it just exponents?
No, for the periodic boundary condition, it keeps growing with time.
I see.
Meaning because there's a continuous input of particles, so the total
I
mass
see.
increases to infinity.
But this
All
is
goes
only in
down.
steady state that you have this.
But in Mustan's paper, they do look at the statistics of the final of the largest mass before it reaches a steady state, and that's a different scaling from the other masses.
I see. Okay.
That obeys extremal statistics.
Yes, yes.
Yeah, one question was that you had considered only this, in this model, the diffusion of the masses as a whole. But if there is also some kind of chipping of the masses, like, so then does it
So if
fundamentally affect?
if you have a model with some chipping also, you can form a condensate there. And then, we have a conjecture for that also. So the answers will change a bit because now the flux, I agree. So in those models also, you can form a condensate and you can have a depletion zone with a different power law that comes different from the bulk. No, sorry. The input is still uniform in the bulk, but when a particle comes to the edge, they hop off. So in the periodic boundary condition, it's like in open boundary condition, there is no reservoir. There's input throughout, uniform input in the bulk, and there's dissipation in the edges. So that induces a mass current from bulk to the edges. Yeah. No, not exact. You can compute the moments exactly as a function of space. Mass, the space-dependent first moment, space-dependent second moment of mass, we can compute, and then based on that, we can find the exponents. Depletion. Yeah, evaporation, for example. So there is a minimal, if you introduce a small amount of evaporation, then there is, it does not affect the answers. But if you introduce a bit too much, then it interferes and you get another phase that comes. But like the thing I told you in the flux, mass flux is there. When you introduce a small evaporation, it messes with that a bit, but does not change the exponents at all.
If there are no more questions, then thank the speaker. So with this, we come to the end of this second session. Thank you.